Welcome to This Explainer. Okay, today we've got an absolutely fascinating paper to unpack. We're going to demystify how tiny, incredibly efficient AI models are completely revolutionizing cancer research and pathology. And honestly, the best part, they're doing all this without needing some massive multi-million-dollar supercomputer. It's really all about bringing cutting-edge medical AI directly to everyday hospitals and clinics. Let's get right into it. Okay, let's dive into this. Here's our roadmap for today. First, we'll look at the clinical pathology bottleneck, then introduce the Flash models. After that, we'll break down how GigaPath-Flash actually works, explore GigaTIME-Flash and spatial proteomics, check out the experimental evidence, and finally wrap up with the impact on precision healthcare. So, whether you're a clinician or an engineer, we've definitely got you covered. So, part one, the clinical pathology bottleneck. Let's set up the massive scale of the problem we're dealing with here. All right, what you're seeing right here is just a standard H&E stained whole slide image tile. But here's the catch, right? A single whole slide image from a biopsy isn't just one of these little tiles. It's made up of thousands of them. We're talking about a gigapixel image. So asking an AI to analyze this whole thing, it's literally like asking someone to read a massive encyclopedia through a microscope. You know, just word by agonizing word, and then somehow expecting them to understand the entire plot of the book. It is computationally exhausting. Which brings us to a huge, massive bottleneck that's blocking population-scale clinical research. How do we actually analyze these gigapixel pathology slides without having to rely on massive, energy-hungry supercomputers? Well, according to the researchers, there are four major barriers holding back current foundation models in pathology. First off, the immense compute cost. Because that tile encoder has to run thousands of times per slide, the teraflops required are just staggering. Second, a lot of these models only look at individual tiles. They completely lack the long-range, slide-wide spatial context needed to actually understand the broader tissue architecture. Third, many models are trained on public, highly curated research data, not the messy, real-world clinical data doctors see every single day. And finally, restrictive licenses prevent a lot of hospitals and researchers from even using them. Solving these barriers isn't just some abstract engineering challenge. It's absolutely crucial for actual patient care. Moving on to part two. Introducing the Flash models. Here is where the solution comes in. And this brilliantly illustrates what we call the metric to medicine translation. So on one side, we have the original GigaPath Foundation model. It's an absolute powerhouse, 1 billion parameters, requiring over 14,000 teraflops of compute per slide. But on the other side is the new GigaPath-Flash. It drops that parameter count all the way down to just 22 million and needs only 290 teraflops per slide. That is roughly 50 times less compute. To put that into perspective, it means hospitals don't need million-dollar server racks to run world-class pathology AI anymore. They can literally do it with much more standard everyday hardware. Okay, part three, how GigaPath-Flash works. Let's peek under the hood at the intuition behind this incredible efficiency. So the whole pipeline breaks down into three pretty digestible steps. First, they used a really clever technique called knowledge distillation. Basically, they took that massive 1 billion parameter teacher model and distilled all its representational quality down into a much smaller 22 million parameter vision transformer or VITS tile encoder. Okay, step two, they paired this with a long-net slide encoder. Now this step is crucial because it looks at all those individual tile embeddings and contextualizes them using dilated attention, which actually scales linearly so it doesn't just crash the whole system. And finally, step three, the end result is a rich, spatially aware, whole slide representation that totally understands the tissue architecture without getting lost in all the complex math. Let's head to part four, GigaTIME-Flash and spatial proteomics. This is applying that same efficient architecture to a massive new breakthrough. Now, what's really interesting about this slide is the sheer visual magic happening here. On the left, you've got a basic, routine H&E stained image. This is the standard tissue slide that every hospital generates. But on the right, you see this vibrant, virtual multiplexed immunofluorescence map, or MIF. GigaTIME-Flash literally takes that basic image on the left and mathematically predicts the complex spatial protein expression. We're talking things like immune cells and tumor markers over on the right. It generates a 21-channel protein activation map directly from a standard slide. So it's virtually creating complex spatial proteomics and doing it without needing the expensive, time-consuming chemical staining process in a physical lab. It's honestly kind of mind-blowing. Which brings us to part five, the experimental evidence. Because the big question is, did shrinking the model 50 times completely destroy its clinical accuracy? Let me draw your attention directly to the top left quadrant of this scatter plot, right here. The horizontal axis is compute cost, so teraflops per slide, and the vertical axis is the average performance score on major cancer grading benchmarks. Now look at that red dot sitting way up in the top left. That's GigaPath-Flash. It is completely isolated from all those heavier models hanging out on the right. It maintains a top-tier average score of 0.826 while using just a tiny fraction of the compute. I mean, this proves that this model punches way, way above its weight class. And the evidence gets even better when we look at the spatial proteomics task. This bar chart compares the original, heavier convolutional neural network model, GigaTIME, in blue, against our new lightweight model, GigaTIME-Flash, in orange. Not only does the Flash model match the original on the test set, it actually outperforms it across the board, especially on out-of-distribution cohorts like brain, breast, colon, and lung cancers. It turns out that foundational model backbone actually improves the model's ability to generalize to completely unseen, diverse tumor types. Wrapping up with Part 6, Impact on Precision Healthcare. So, what do all these incredible technical wins actually mean for doctors, researchers, and ultimately, the patients? So the crucial point is captured perfectly right here. Let's just look at what happens when a hospital tries to process a large batch of slides, say a batch size of 128. The original model plateaus at around 390 tiles per second, and it eats up almost 17 gigabytes of GPU memory. But GigaTIME-Flash, it absolutely blazes through nearly 1,700 tiles a second and uses just over 2 gigabytes of memory. That's 8 times less memory and 4.6 times faster throughput. It means that generating virtual biomarkers for an entire population of patients isn't just some pipe dream for research labs anymore. It's a practical, everyday reality for almost any hospital with a standard clinical workstation. And that leads us to probably the most powerful aspect of this entire paper. The researchers didn't just build this and lock the technology away. They actually released the entire GigaPath and GigaTIME family under an open-source Apache 2.0 license. Like they say right here, they are providing accessible and efficient building blocks for the future of precision health. And honestly, it forces us to ask a final provocative question. If every hospital in the world, regardless of their computing budget, can suddenly run state-of-the-art foundation models to analyze the tumor microenvironment, how fast will we accelerate the cure for diseases we once thought were totally unbeatable? Thank you so much for joining me for this explainer, and I highly encourage you to read the full paper to see how this democratization of AI is really unfolding.